In this video, we're going to look at solving simultaneous equations using what's known as the matrix method. So here we've got two straight lines determined by these sliders of the type ax plus by is equal to c. So this is x plus y is equal to 0, this line here. And here we have the line cx plus dy is equal to f. So we've got minus x plus y is equal to minus 1 here. Again, this GeoGebra applet I will put in the notes of the video, the link, so that you can get it. So if you're solving them, you'd set them out like this. X plus y is equal to 0 and x plus y is equal to minus 1. And we do some sort of substitution or elimination. But it is possible to solve them by a matrix. So what you can do, you should take the coefficients. Here we've got the coefficient 1, 1, minus 1, 1. So we've got 1, 1, minus 1, 1. Multiply it by x, y, and that's equal to 0, minus 1. Now, if you think when you multiply matrices, you do a row times a column. So it's going to be 1x plus 1y will be equal to 0, which will give you that. And then you've got this row times this column, so that'll be minus x plus y is equal to minus 1. So it does make sense that you can put them in a matrix. And if you can solve this matrix for x and y, you can actually find the value of x and y. Now the theory for this you can get by just looking up this. So if you've got some variable x and you pre-multiply it by the matrix M and it's equal to some other matrix A, which is what we've got over here. If you multiply, find the inverse of M, this is for 2 by 2 matrices, but it works for 3 by 3 as well. Find the inverse of M, which is M to minus 1 times X, and do the same to the other side, but you need to pre-multiply this one. You can't post-multiply it because matrices, the order of matrices is not commutative. Okay, so if M is equal to A, B, C, D, then the inverse can be found by swapping A and D over, so get D and A, and then changing the sign on B and C, but you have to multiply by 1 over the determinant, and the determinant here will be 1 over AD minus BC. So the determinant here will be 1 times 1 minus minus 1, which is actually 2, so 1 over 2. Now, if you take a matrix and multiply it by its inverse, it's like doing the identity. And the identity matrix for 2 by 2 matrix is 1, 0, 0, 1. If it's 3 by 3, it'd be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and then if you do the identity times x, you get x. So all you need to do to find x is take the inverse of the matrix and multiply it by the other matrix. So this is what we've done here. We set up our matrix equation here, then we have pre-multiplied both sides by the inverse matrix. So basically I'll swap the 1 and 1 over, that's quite easy. The signs of these two here have changed, and I found 1 over the determinant. The determinant I've already told you is 2, and I've done the same here. If I do that here, I get 1, 0, 0, 1 times xy, and this will be equal to, if I multiply this out first, I'm going to get 1 times 0 times 1 times minus 1, which gives me 1. And then 1 times 0 plus 1 times minus 1, which gives me minus 1. And I get a half. And then take the half in. Always do the half at the very end, yeah? And a half will give me 0.5 minus 0.5. So that gives me x is 1/2 and y is equal to minus a half. And then I get the result here. Now I can move the sliders around on this applet and get other equations. We'll look at that as one of those cases there. There's something a bit more complicated. Okay, so here the determinant will be minus 5 times 1, which is minus 5, minus minus 1. So minus 5 minus minus 1 is minus 4. Swap the 2 over, so 1 and minus 5, and then swap the signs on the other two. We've done that. And do the same to both sides. Okay, and then work through it. I always advise you here to multiply this one by this one and then do the minus a quarter at the end in this case. Okay, so it gives minus a quarter, minus 5, and obviously when you're solving simultaneous equations, you're finding where they actually meet. So it does give us a different way of doing it. So we can change this one as well if we want to be different values. There's something even more complicated. Now the interesting thing to do is, does it always work? Well, let's have a look at this situation. Let's see if I can organise that for us. So let's do this. Let's make A2 B3, and let's do the same here. C2 and B3. Okay. Let's just make this like that. Okay, so here we've got 2x plus 3y is equal to 3 and 2x plus 3y is equal to minus 1. The lines are parallel. So there are no solutions to this problem. Now, the reason why there'll be no solutions in the matrix method, what happens is, for some reason we've got that there. We'll move that out. Okay, so the reason here is that here we've got 2x plus 3y, 2x plus 3y is equal to 3 minus 1. So we've got 2, 3, 2, 3. If you take the determinant, 2 times 3 minus 2 times 3, it's going to give you 0. And obviously 1 divided by 0 you can't work out. Therefore, you're not going to get any solutions. Okay? So this is what happens when lines are parallel. Now, when lines are the same thing happens. The line could coincide. The only thing is the two numbers at the end will be the same. Okay, so this has been a video to show you about solving simultaneous equations using the matrix method. Now, this method is used a lot more when you have when you're doing lines when you're doing planes in 3 dimensions. This is probably a more useful way of doing it than using elimination or substitution. Okay, I hope you've understood. The GeoGebra app I will put in the notes of the video, and I thank you very much for watching.